Today, let's start by talking about the architecture of the large clusters and supercomputers used for scientific discovery. If you've ever seen pictures of these machines, they look fabulously complicated with all sorts of crazy connections and wires all over the place. But really fundamentally, they're the same computers that you have on your desk. It's just a large number of them, all connected by a network. So today I'm going to explain how a large cluster is built up from simple components. Let's start by looking at the fundamental component of a cluster, which we'll call one node, or sometimes one machine. So by one node, we mean a single container that contains one or more CPUs, some memory, and some local storage. Those CPUs, the central processing units, are the same sort of processors that you would find in your desktop or your laptop machine. Sometimes they're a little bit slower, maybe in the 1 gigahertz to 2 gigahertz range, rather than the very fast processors you might have, simply because it's more economical to buy a large number of slower processors than a small number of faster processors. Each of those processors will also have multiple cores. So if we had 4 CPUs, each with 4 cores, you might have a 16-core machine. In addition to those CPUs, a high-performance machine is also likely to have a graphics processing unit, a GPU, or some other accelerator device like an FPGA. And each one of those devices is likely to have hundreds of modestly powered cores. Each of those cores is going to share some random access memory, and there will also be a storage device of some kind. Historically, those storage devices would be a hard disk drive, which contains of a spinning disk and some moving hardware on a magnetic disk. But more recently, those have been replaced by solid-state disks, or SSDs, which accomplish the same storage without moving parts. And you take all these pieces, they're the same components you would have in your desktop computer, they're just going to be packaged a little differently into a container we sometimes lovingly call a pizza box, just because it's wide and flat, but apart from that, it's just one conventional computer. Now, to scale up, we're going to take a bunch of these nodes and start to stack them into one rack. There's a standard size physical rack that's used in all data centers for this size of equipment, and it has 42 slots, so it's known as a 42U rack. A typical node might occupy 1 or 2 or 4 slots in that rack, so it's called a 1U or a 2U or a 4U computer. And one rack is going to hold all those computers, as well as all of the networking and power and other cabling necessary to support those machines. Now, the machines by themselves can't do much work. They need to communicate with each other. So they're going to be connected by some networking equipment. And typically, we would put a network switch at the top or the bottom of that rack, and then connect all the machines together into that single switch. Now, there's a variety of technologies out there. Standard Ethernet, the same thing you would have on your desktop computer, is used on small clusters, whereas there's also some high-performance network technologies, such as InfiniBand, that would be used on the most high-performance machines. Now, one rack is filled up with a large number of machines and networking capability. And now, by using multiple racks, we can build out a cluster to almost arbitrary size by simply duplicating those racks. And they typically just get stacked up next to each other in a data center that has a large amount of cooling and air conditioning capacity in order to keep them cool. Now, each rack has its own switch, but then to connect them all together, we need one switch or router, or possibly multiple, that will connect each of those top-level switches and allow for communication between the different racks. Now, while that one switch on each rack may be relatively modest, the switch or router that's going to connect the whole data center has to be a very high-capacity, very high-performance device in order to handle the traffic generated by all of the racks. Now, each of these nodes provides the computing, and although they do have some amount of local storage that they may use to load the operating system or handle temporary data, typically we need a different place in order to store the large data shared across all of the cluster. So in a large cluster, we would set aside some number of racks that we would call storage nodes. And in these storage nodes, they would also be machines, but those machines would be equipped with a very large number of disks, maybe 8 or 16 per node. And then this is where we would run a database or a file system in order to provide storage services for the rest of the cluster. Now, as you might expect, if all our data is over here and all our computing is over here, then there's going to be a lot of communication over these networks in order to get the data to the machines and vice versa. However, there's a good reason for separating out all these storage nodes. If that data is of high importance and requires special techniques to manage, we want that to be all in one place so we can manage it carefully. Now, once we've built out a cluster, there are 2 broad ways of doing computing on this cluster, and they're known as HPC and HTC. HPC stands for high performance computing, and HTC stands for high throughput computing. They're similar, but they're different approaches, although they can be mixed within the same cluster. HPC is known as high performance computing, and usually the goal of HPC is to accelerate a single large application by taking that application, breaking it up into pieces, and then running all the pieces simultaneously across the nodes of the cluster. And our goal here is to get that one application to run as fast as possible without regard to anything else that's going on. So here, if we had our picture of the cluster, in HPC you can think of taking one large application, spreading it across, and using the entire cluster if possible to run that one large application if possible. HPC is the dominant mode of computing for things like weather simulation, or for simulation of fluid flow, or for simulation of very large domains in which we need to exploit the distributed memory of the machine in order to store everything in the simulation simultaneously. Often what we talk about in terms of supercomputers is application to high performance computing. So HPC is one mode. The other mode is HTC, which is high throughput computing. Now the goal of high throughput computing is a little different. The goal of high throughput computing is to complete as many units of work as we can in a given amount of time. And that's different than trying to run one unit of work as fast as possible. So our metrics of success in high throughput computing are things like how many frames of animation can we render in a week? How many simulations can we complete in a month? Or how many genomes can we analyze per year? And if that's our goal, then we might break up our work in a different way than HPC. So with HTC, what we're going to use is try to use each of the nodes of the system independently such they can then each run a different application. So if we took that same cluster and we used it in a high throughput computing style, we would have one application on each machine, each running independently. Now, HPC and HTC are kind of two sides of the same coin. They're different ways of thinking about a cluster, and you may choose to do one or the other depending on the shape of your application. HTC is probably the better choice if your application can fit on a single machine. But if your application requires the distributed memory of many machines, then HPC is the better way to go. So here's an example of high throughput computing. Suppose that I want to better understand the behavior of a complex molecule by performing a distributed simulation. Now, I'm going to simulate how that molecule behaves by working out the Newtonian mechanics between every single atom in that molecule. And if I introduce some random numbers, then that molecule is going to bounce around in a different way every single time I run that simulation. So now running one simulation by itself tells me something, but it doesn't tell me a lot because it only shows one way in which that molecule could move around. If I really want to understand the whole behavior of the molecule, what I have to do is simulate it at multiple different temperatures. And each time I simulate it at different temperatures, maybe I have to run that simulation 100 times in order to accumulate statistics on how it behaves. And then on top of that, maybe I'm interested in the behavior of 3 different molecules. So I'm going to run 3 different molecules at 10 different temperatures times 100 different simulations. And now I have a very large amount of simulation to do, but every single one is independent. And so I can dispatch each one to a different node in the computer. And that's high throughput computing because each simulation can run independently. So it doesn't matter whether I run 10 at a time or 100 at a time or 1,000 times, they can all be dispatched to each node of the simulation independently. That's high throughput computing. So to wrap up, whether we're doing HPC or HTC, the key is to find concurrency at one or more levels within an application. Concurrency is the potential for multiple things to happen simultaneously and therefore independently. So if we can take our workload and divide it up so that each concurrent part can execute on a different node in the cluster, then we'll be able to use it efficiently.